Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. Let me introduce myself. I am Yudhistira di Putra as the presenter of this project in this international conference on industrial, mechanical, and chemical engineering. There are two other authors. There are Mr. Ahmad Fauzan Zakki and Mr. Andi Trimulyono, are also from Diponegoro University Naval Architecture Department. Going up to our project, the project title is Design of Kaplan-series Propeller for Commercial Submarine by varying rake and number of the blade to obtain the highest thrust and efficiency. Let me show you what is it about. Nowadays, the submarines is not only used for the military but also for the oil and gas industry. Therefore, the need for submarine is increasing year by year. The submarine's capability to operate beneath the ocean depends on air-independent propulsion. This kind of propulsion cannot consume ordinary fuel. Polyelectrolyte membrane fuel cells are arranged on board. This kind of fuel cell is much more expensive than the usual marine fuel. However, it is a desire to design the propeller that has the highest thrust and efficiency. There is a limitation of the time how long submarine could dive in. With a better propeller efficiency, it could extend the bottom time of itself. From the previous study, we know that applying nozzle could increase the efficiency, and from another paper that I mentioned in my paper, the Kaplan-series propeller could be better than B-series propeller. So we decided to take a study for Kaplan-series and DUX type 19A. That's all the introduction of this project. Going up to theoretical background. This research will carry out a computational fluid dynamic simulation on Kaplan-series arranged with its submarine's hull to capture the behavior that produced due to the change in the number of blade and rake angles on the submarine propeller and to obtain the performance of the thrust, torque, and propeller efficiency. Those are the equations used to solve the flow simulation. Computational fluid dynamics based on the incompressible Reynolds average never stock used to carry out the flow simulation. The propeller model has the characteristic that describe its hydrodynamic ability. The result that has been computed by CFD usually refers to thrust, torque, and efficiency. The hull form from the previous study was used in the present study. The ship's resistance was obtained 40.7 kN and 8.2 knots based on the previous study. Kaplan-type propellers are chosen because they tend to have higher thrust. The parametric studies are about the rake angle and blade number. The number of the blades were used 6, 8, and 10. This difference aims to find the highest thrust. Rake angles are also divided into 5, 10, and 15. Going up to the modeling section. After the component had been drawn, we are modeling the cross-section of the DUX 19A into a 3D model. The propeller is designed to be arranged with a nozzles. The previous study concluded that DUX 19A has a desirable hydrodynamic feature and easy to fabricate. As a result, nozzle 19A is chosen to use in simulation. This figure is present the DUX 19A. After the component had been drawn, nozzle need to be joined to hull form. Therefore, NACA foil 0018 was chosen to arrange on board. After all of the components had been drawn, the propeller and its nozzle need to be joined to hull form. The hull form of a submarine is presented by this figure. Going up to the computational domain, CFD simulations are followed by the criteria of ITTC CFD guidelines. For the case of the propeller domain, two fluid domains need to be created, which is the fluid domain and the propeller domain. This simulation was uses a steady state condition. The fluid domain is created with the dimension that suggested by ITTC. The inlet boundary is defined as a velocity inlet which has speed as same as the submarine speed. The outer tubular wall is defined as an opening. It allows the fluid to cross the boundary surface in either direction. The outer boundary is defined as an outlet pressure. The submarine itself is defined as a no-slip wall, so the velocity of the fluid at the wall set to 0. This mesh independence has been generated to ensure an adequate number of self-meshing that were sufficient used for all simulations to obtain accuracy and steadiness in the computational result regardless of the longer CPU time. However, the total number of self-meshing with about 2 million was selected for all simulation due to reliability mesh result in capturing the flow field and pressure distribution on the blade surfaces. Going up to the result, this is the result from the torque from the thrust. This is the result from the torque, moment, and the result from the efficiency. Among all 9 simulations, we can conclude that the parameters that have been reviewed in this study using CFD method on submarine propellers showed the propeller characteristic. The increase in rake angle tends to increase thrust, torque, and efficiency. It was also found that increasing the number of propeller blades showed consistent increasing torque and decreasing efficiency, while the thrust stance did not show homogeneous result. The phenomena occur varies by increasing the number of the blade. Among all propeller tested, the Kaplan-1080 propeller with a rake angle of 5 degrees is a propeller with the highest thrust and torque. There are 201 kN and 181 kN-meter. 181 kN metric. On the other hand, the propeller with the highest efficiency is the Kaplan 680 rake 15 degrees with an efficiency reaching 50.9% at 100 revolution per minute. These two figures present the simulation among all 9 simulations. That's all of the presentation of our project. Thank you very much for your attention.